Welcome to today's lesson on machine learning, where we will explore logistic regression. This important topic promises to provide valuable insights into classification problems. Let's dive into the lesson, which will begin on the following slide. Welcome to our exploration of logistic regression, a crucial technique in the field of machine learning. In this presentation, we'll delve into the intricacies of this powerful algorithm and understand why it has become a go-to choice for tackling classification problems. First, let's address the burning question. Why logistic regression? This technique shines when we need to predict discrete outcomes, such as whether an email is spam or not, or whether a patient is likely to have a certain disease. Its ability to model the probability of an event occurring makes it an indispensable tool in various domains. Next, we'll dive into the nitty-gritty of the logistic regression model. We'll explore how it leverages the logistic function to transform linear combination of input features into probabilities. By understanding the underlying mathematics, we can gain a deeper appreciation for its elegance and effectiveness. Of course, to make our model truly useful, we need to estimate its regression coefficients. This is where the concept of maximum likelihood estimation comes into play. We'll discover how this powerful technique allows us to find the optimal values for our model's parameters, enabling it to make accurate predictions. But the power of logistic regression doesn't stop there. We'll explore its various extensions, such as multiple logistic regression, which enables us to handle multiple predictor variables seamlessly. We'll also touch upon multinomial logistic regression, a variant that allows us to classify data into more than two categories. Finally, we'll take a step back and see how logistic regression fits into the broader context of generalized linear models. By understanding this connection, we can appreciate the flexibility and adaptability of this technique in tackling a wide range of problems. So, let's embark on this journey together and unravel the secrets of logistic regression. By the end of this presentation, you'll have a solid grasp of its concepts, techniques, and applications, empowering you to leverage its potential in your own machine learning endeavors. In today's data-driven world, understanding the relationship between variables and predicting outcomes is paramount. This is where logistic regression comes into play. As a powerful statistical modeling technique, logistic regression allows us to model the probability that a response belongs to a particular category. Imagine you're a financial institution assessing the risk of loan defaults. Logistic regression becomes your ally in this endeavor. By leveraging this technique, you can model the probability of a loan default based on various predictors, such as credit score, income, and employment status. This empowers you to make informed decisions and manage risk effectively. At the heart of logistic regression lies the logistic function, a mathematical marvel that transforms the relationship between the probability of response and the predictors. This function elegantly maps the input variables to a probability value between 0 and 1, providing a clear and interpretable output. Logistic regression's versatility extends beyond binary classification. With extensions like multinomial logistic regression, we can tackle scenarios where the response variable has more than two categories. This opens up a world of possibilities, from predicting customer churn to classifying email spam. Moreover, logistic regression forms a vital component of the broader family of generalized linear models. By understanding this connection, we can appreciate the flexibility and adaptability of logistic regression in handling a wide range of data types and distributions. As we delve deeper into the realm of logistic regression, we unlock its potential to revolutionize decision-making processes across industries. From healthcare to marketing, from finance to technology, the applications are limitless. By harnessing the power of logistic regression, we can uncover hidden patterns, predict outcomes, and drive strategic initiatives with confidence. So, let us embrace logistic regression as a key tool in our data science arsenal. As we navigate the complexity of a data and strive for meaningful insights, logistic regression stands as a beacon, guiding us towards accurate predictions and informed decision-making. In the realm of predictive modeling, two powerful techniques stand out: linear regression and logistic regression. While both aim to uncover relationships between variables and make predictions, they serve distinct purposes and cater to different types of response variables. Linear regression, a stalwart in the world of statistical modeling, excels when the response variable is continuous in nature. It seeks to establish a linear relationship between the predictors and the response, enabling us to estimate the value of the response based on the given predictors. This makes linear regression an invaluable tool for tasks such as predicting housing prices or forecasting sales revenue. On the other hand, logistic regression shines when the response variable is categorical, typically binary. It models the probability of the response belonging to a particular category based on the predictors. Unlike linear regression, which outputs a continuous value, logistic regression provides a probability estimate between 0 and 1. This makes it ideal for classification problems, such as predicting whether a customer will churn or whether an email is spam. The key difference lies in the nature of the response variable and the underlying assumption. Linear regression assumes a linear relationship between the predictors and the response, and the errors are assumed to follow a normal distribution. In contrast, logistic regression does not assume linearity and models the log odds of the response as a linear combination of the predictors. While linear regression minimizes the sum of square residuals to find the best fitting line, logistic regression uses maximum likelihood estimation to estimate the coefficients that maximize the likelihood of observing the given data. It's crucial to understand the strengths and limitations of each approach. Linear regression is interpretable and provides a straightforward way to quantify the impact of predictors on the response. However, it may not be suitable when the relationship between the predictors and the response is nonlinear or when the response is categorical. Logistic regression, on the other hand, is specifically designed for categorical responses and can handle nonlinear relationships. It provides a probabilistic interpretation of the results, making it valuable for risk assessment and decision making. However, it assumes that the predictors are linearly related to the log odds of the response, and violations of this assumption can impact its performance. Choosing between linear regression and logistic regression depends on the nature of the problem at hand. By understanding the characteristics of the response variable and the goals of the analysis, we can select the appropriate technique to unlock valuable insights and make accurate predictions. In the ever-evolving landscape of data science, mastering both linear regression and logistic regression is essential. By leveraging their strengths and applying them judiciously, we can tackle a wide range of real-world problems and drive data-driven decision-making. So, let us embrace the power of these regression techniques, armed with the knowledge of their unique capabilities. As we navigate the complexities of data, linear regression and logistic regression stand as indispensable tools in our arsenal, empowering us to uncover hidden patterns, make precise predictions, and propel our organizations forward in the age of data-driven innovation. In the dynamic landscape of data analysis, logistic regression has emerged as a powerful tool for tackling binary classification problems. However, in real-world scenarios, we often encounter data sets with multiple independent variables influencing the outcome. This is where multiple logistic regression comes into play, extending the capabilities of simple logistic regression to handle more complex relationships. Multiple logistic regression, a close cousin of multiple linear regression, allows us to model the relationship between a binary dependent variable and multiple independent variables. By considering the combined effect of these predictors, we can gain a more comprehensive understanding of the factors driving the outcome and make more accurate predictions. The beauty of multiple logistic regression lies in its ability to capture the intricate interplay between multiple variables. It enables us to assess the individual contribution of each predictor while controlling for the effects of others. This is particularly valuable when dealing with real-world datasets, where multiple factors often influence the outcome simultaneously. Multiple logistic regression opens up a world of possibilities across various domains. In healthcare, it can be used to predict the likelihood of a patient developing a certain disease based on multiple risk factors. In marketing, it can help identify the key attributes that influence customer churn. In finance, it can assist in assessing the probability of loan default, considering multiple borrower characteristics. However, it's crucial to be mindful of the assumption and limitation of multiple logistic regression. The model assumes that the log odds of the outcome are linearly related to the predictors, and violation of this assumption can affect its performance. Additionally, the model is sensitive to multicollinearity, where high correlation among predictors can lead to unstable coefficient estimates. Despite these considerations, multiple logistic regression remains a potent tool in the data scientist's arsenal. By leveraging its capabilities, we can unravel complex relationships, make accurate predictions, and drive data-driven decision-making in a wide range of applications. As we navigate the ever-expanding landscape of data, multiple logistic regression serves as a beacon, guiding us towards a deeper understanding of the factors shaping binary outcomes. By harnessing its power, we can unlock valuable insights, optimize strategies, and propel our organizations forward in the age of data-driven innovation. So, let us embrace the potential of multiple logistic regression, armed with the knowledge of its strengths and limitations. As we tackle the challenges of binary classification in the presence of multiple predictors, this technique stands as an indispensable ally, empowering us to make informed decisions and drive meaningful change in a data-driven world. In the vast realm of categorical data analysis, multinomial logistic regression emerges as a powerful tool for tackling classification problems with more than two possible outcomes. While binary logistic regression focuses on dichotomous response variables, multinomial logistic regression allows us to model the relationship between a nominal dependent variable and multiple independent variables. Imagine you're a marketing analyst tasked with predicting customer preferences for a new product line. The customers can choose from three distinct options: product A, product B, or product C. Multinomial logistic regression becomes your go-to technique to unravel the factors influencing these preferences and make accurate predictions. At its core, multinomial logistic regression extends the concept of binary logistic regression by considering multiple logic equations simultaneously. Each logic equation compares the probability of a specific category to a reference category, typically the last category. This allows us to estimate the odds of a data point belonging to a particular category relative to the reference category. The beauty of multinomial logistic regression lies in its ability to handle multiple predictors seamlessly. By incorporating variables such as age, income, and gender into the model, we can assess their individual and combined effects on the categorical outcome. This holistic approach enables us to identify the key drivers behind customer preferences and make data-driven decisions. Multinomial logistic regression finds applications across various domains. In healthcare, it can be used to predict the severity of a disease based on multiple patient characteristics. In finance, it can assist in classifying loan applicants into different risk categories. In natural language processing, It can help identify the sentiment of a text document among multiple sentiment labels. However, it's crucial to be mindful of the assumption and limitation of multinomial logistic regression. The model assumes that the categories are mutually exclusive and exhaustive, and the relationship between the predictors and the log odds is linear. Violations of these assumptions can impact the model's performance and interpretability. Despite these considerations, multinomial logistic regression remains a valuable tool in the data scientist's toolkit. By leveraging its capabilities, we can unravel complex relationships, make accurate predictions, and drive informed decision-making in a wide range of applications. As we navigate the ever-expanding landscape of categorical data analysis, multinomial logistic regression serves as a guiding light, illuminating the path towards a deeper understanding of the factors shaping multi-class outcomes. By harnessing its power, we can unlock valuable insights, optimize strategies, and propel our organizations forward in the age of data-driven innovation. So, let us embrace the potential of multinomial logistic regression, armed with the knowledge of its strengths and limitations. As we tackle the challenges of multi-class classification, this technique stands as an indispensable ally, empowering us to make informed decisions and drive meaningful change in a data-driven world. In the ever-evolving landscape of statistical modeling, generalized linear models, GLMs, have emerged as a comprehensive framework for analyzing and predicting relationships between variables. Among the various techniques within the GLM family, logistic regression stands out as a powerful tool for binary classification problems. However, the scope of GLMs extends far beyond logistic regression, encompassing a wide range of models tailored to different types of response variables and data distributions. At the heart of GLMs lies the concept of the conditional distribution of the response variable. In contrast to traditional linear regression, which assumes a Gaussian distribution, GLMs allow the response to follow various parametric families. This flexibility enables us to model diverse types of data, from binary outcomes to count data and beyond. In the realm of linear regression, the response variable is assumed to follow a Gaussian distribution, making it suitable for modeling continuous, normally distributed data. However, when dealing with binary outcomes, such as predicting the presence or absence of a condition, logistic regression takes center stage. In this case, the response variable follows a binomial distribution, and the model estimates the probability of the outcome belonging to a particular class. The link function is a crucial component of GLMs, defining the relationship between the model parameters and the linear predictor. In logistic regression, the link function is the logit function, which maps the probability of the outcome to the log odds scale. This transformation allows us to establish a linear relationship between the predictors and the log odds, enabling straightforward interpretation and estimation of the model coefficients. However, the power of GLMs extends beyond logistic regression. When dealing with count data, such as the number of events occurring within a specific time interval, Poisson regression comes into play. In this case, the response variable follows a Poisson distribution, and the link function is typically the log function. By modeling the logarithm of the expected count as a linear combination of the predictors, Poisson regression provides valuable insights into the factors influencing the occurrence of rare events. Another notable member of the GLM family is gamma regression, which is particularly useful when the response variable is continuous, non-negative, and positively skewed. The gamma distribution is characterized by its shape and scale parameters, and the link function is often the inverse or log function. Gamma regression finds application in various domains, such as modeling insurance claims or analyzing survival times. The beauty of GLMs lies in their ability to accommodate a wide range of data types and distributions while maintaining a consistent framework for estimation and inference. By selecting the appropriate distribution and link function, we can tailor the model to the specific characteristic of the data at hand, enabling accurate predictions and meaningful interpretations. As data scientists and analysts, it is essential to have a deep understanding of the GLM framework and its various components. By leveraging the power of GLMs, we can tackle a wide range of real-world problems, from predicting customer churn to analyzing disease progression. The flexibility and extensibility of GLMs make them an indispensable tool in our analytical arsenal. In the era of big data and complex decision-making, GLMs provide a solid foundation for data-driven insights. By mastering the concepts of conditional distributions, link functions, and the diverse family of models within the GLM framework, we can unlock the full potential of our data and drive meaningful change across industries. So, let us embrace the power of generalized linear models. Armed with the knowledge of their versatility and adaptability, as we navigate the challenges of modeling diverse data types and distributions, GLMs stand as a unifying framework, empowering us to extract valuable insights, make accurate predictions, and propel our organizations forward in the age of data-driven innovation. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.